Hello. In this video we will calculate a wall. This is the wall. The wall is supported by beam and the beam is supported by bore piles and subsoil. The goal of the calculation is to input line load on the top of the wall and transfer the forces directly to this beam. It means we should get following model: beam supported by simple supports, also supported by subsoil, and loaded by line load. The line load could be minus 10 kilonewton per meter. If we do it with standard FEM analysis, then in this analysis we have finite elements. And the finite elements get also deformation in shear. So they will transfer the force from top to bottom, but because we have non-constant supports, then we get also these deformations, and the elements get also deformation. That means the stiffness, the shear stiffness in the wall, which is used in the stiffness matrix as small d33, will influence the transfer of the forces, and we don't get so much forces on the beam, and more of the forces will go to the bore piles. What can we do? We have three possibilities. The first one is to reduce the shear modules, maybe to 0 or to very small value. If we do it, what happened? We reduce the stiffness of the wall, but in 3D, if you look at the wall, this is the wall, and the wall will be loaded by forces which are perpendicular to the wall, then also the elasticity modulus for the shear will be used. So if we reduce it to 0, then we also influence the bending of the wall. The second possibility is to use so-called property modifier in SciEngineer, and we will reduce the D33 stiffness. The minimal value which we can use is 0.01. Sometimes it's not enough. Sometimes also the forces goes, this is too much, and the forces goes then to the beams. So the third possibility is to use orthotropic properties, and then we can reduce D33 also to 0 or to very small value. The property modifier is only a factor which is used to multiply the original stiffness of the elements. So and now we go to SciEngineer. Okay, now we create an analysis model directly in SciEngineer. I start a new project, select the material concrete and reinforcement. So I'm using Eurocode, but for our calculation it has no influence. Okay, without any another settings, we use general XYZ model, and please don't forget the project level every time to change to advanced. Now we are in an empty project, and I create for start a line grid to draw the wall quicker and to have some dimension lines directly on the screen. So 2.5, 1.5, 1 and, oh, excuse me, 2.5, 1.5, 1 and 0.5. Okay, 6.5 in X direction, and in Z direction we have the beam, and then the below the window, then the height of the window, then on the top of the window 3.5 meters. Okay, change to XZ, put off the grid labels and the labels. Okay, and put it on 0. Enter. Escape and close the line grid. Now I can switch to Y direction. It's not bad also directly to switch the working plane to XZ. And now we can draw the structure. I use 2D member. It doesn't matter if you use plate or wall. So I see the command line, it is not okay, now we see the command line. It doesn't matter, I go to plane, 200 millimeter is thickness, and we should start in the middle of these 2 points, because this is the axis of our beam. So we have activated the tracking. I push the shift button on the keyboard, go to this point, go in this direction and write 0.25. Okay, and now I push shift, select this node, and then this is my endpoint. Okay, endpoint, endpoint. It's finished. Now we can add an opening through these 4 points, and the next one between this and this point. So I select with shift this point, and this is my start point. Go in this direction, 2.25, then with shift to this point and shift, this point is the end point. Okay. It doesn't matter if you create openings, you can create it a little bit bigger. This is not a problem. Sometimes better than you try to get the line directly. Okay, now we need the beam, 1D member, rectangle with the height of 500 millimeters and the width of 1000 millimeters. This is the supporting beam. Okay, from this point to this point. So, and this is then our model in Y direction. Okay, supports left, right. I will put off the X direction so that it can move in X direction, and I will store the rotation around X axis, so now it's rigid, and then the wall cannot keep. So because if we don't do it, then the wall can go in this direction. Okay, now we need the line support below of this beam. There are 2 possibilities, but this is not the goal of this project. Model data support, I use line on beam, and in X direction it's free, Y direction could be rigid, Z direction is flexible, and we use 35 meganewton per meter length, meter depth, and because the width of our support is 1 meter, then it's the same like the Winkler constant of 35 meganewton. And the rotation is free, and around Y-axis is rigid. Okay, it's correct. Around X-axis it should be rigid. So, and around Y-axis free. Okay. Okay, that's the first model. The second model is only the beam with the supports. I copy it from, you can say from this point in this direction 10 meters. Okay. And now we create load case, not self-weight. This is not interesting for us. I input directly line force on 2D members edge in a global coordinate system minus 10 kilonewton per meter. We can put on the labels. Okay. And the same on the beam, minus 10, and in global coordinate system. Okay. Put on the supports and off the dot grid. Okay. Then the model is finished, and we can run the calculation with the mesh setup. This is a very small model, so I can say 20 centimeter is the size of our 2D element. There is also one important thing. We have with subsoil supported beam, and the length of the finite elements for the beam could be defined in this row, so we can also say 20 centimeters. Okay, and run the calculation. After the calculation, we can compare the results. From the results, we can select the reactions. RZ, but not the, oh, this is extreme in node. There's something wrong. Yes, I don't have the support on the right side, so I have to copy this support. Where is it? Copy additional data to this node. Okay, and on the left side, no, there is also missing. Maybe it was put it off. No problem. We can copy it and run the calculation again. Okay, I don't need the thickness. And look on the results. Reactions. Okay. 28 kilonewton and 14 kilonewton. And if we look also on the reactions between the points, we see 1.6, and here is only 0.3, 0.4. Because in this wall, before the load comes from top to bottom to the wall of the wall, it will be distributed to the points which are stronger. We see it on the displacement, deformed structure. That's too high. You see, these supports are rigid, so all forces are going to these supports. Maybe we will see it in 2D member, internal forces, and we use the principal magnitudes, the N1. N1, this is the main norm axial force, and we don't use the standard, we look on the trajectories. So nice. And here you see where the forces are going. They are going here and here in these points. Okay, we want to change it, therefore I select this structure, make a copy of them, go in this direction for 7 meters. Okay, the supports are also there, and I make a next copy from left to right with 10 meters. Okay, and we change it by 2 ways. First, I activate the property modifier, and if the property modifier is activated, we can go to the structure, and in model data we see the property modifier for 2D, and I can change the correction factor for D33, and this is the shear stiffness of a wall element. So I think the minimum is 1%, 0.01, try 0.001, no, 0.01 is the minimum, okay. And we put it on this wall. And now we compare the results. First, we compare the reactions. So, again, it's too much. I think I don't need the line grid anymore. I put this off. Okay, it's better. So, 28, 27, 14, what we have here, 18 is much better. And here 1.3, 0.3, and here we have 1.6. So we are closer to this model, but not very close, because we still have stiffness, the shear stiffness. We see it on the displacement. There is much smaller stiffness, but there is some, because if we don't have stiffness in these elements, then this deformation goes to infinity. And this will be also the problem on this model if we change the stiffness to 0. If I go to structure and change the wall to an orthotropic wall, then I can change the orthotropic properties. And on the same way, like with the stiffness modifier start with this value. This is 1. So we can make it smaller to 1%. So from 1000 to 1. But with the orthotropic properties, we can go also to 0. I will not go to 0. I reduce the stiffness to 1000, so 1 promille. And look what happened. I think we will need extra beams, so we have more deformations. Look at the deformations. So they are much larger than here, but it's still, we don't have instability. And if we compare the reactions, 16, 14, 18. So I would say this is okay. We can compare the internal forces on the beam and the maximum value for each member. So we see 11, 16, 16, 18. So I think this one of these models could be used. So you never get this value because we have openings. So and the forces are going not through the openings. They are going in this direction. So we can see it on 2D member internal forces. I hope it's still changed. Okay. So you see where the forces are going. Yes, they are going here in this direction down. But we can change it also to 0. We can go again to orthotropic properties, and I can reduce the stiffness for shear to 0. And now we get an instability in the model. You see very large deformations. So we have to do something with it. We see the results. Displacements. So they are very large, very high. So it's in one direction. So we need to fix these deformations. We go to structure, to the model data, to supports, line onto the member edge, and we have to support these two lines in the horizontal direction. We don't need Rigid support, it could be flexible with very small stiffness, 0.1, and all other could be free. So that's the first thing what we have to do. So what is the direction? Global coordinate system. Okay. And now we also have to support these two lines with beams. We create a new cross section, maybe 20 to 20 centimeters. And add a beam with the 20-20 cross section on this line and also on this line. And now we can calculate again. Results. So first check the reactions. You see 14, 18, 16, bending moment 1.6, 1.6. Oh, this is the reaction. And look on the bending moment. 18, 16, 16. So it's near the same in all models. You see there is no much difference between these two models. So I would say the working with the property modifier is on the safety side, because you don't need to watch all these instabilities as with the orthotropic parameters, because if you in orthotropic parameters reduce the stiffness to 0, then you can make small troubles. Okay, it was. Thank you for watching this video, and I hope I see you at next video. Thank you and bye.